Alright. We are on episode 20, number 20, in our video series going from a noob to a veteran ASM coder. This is going to be our first episode regarding the pro level tier threads. You're getting near to the end of your journey. You've been learning a lot, so now let's get into the really advanced stuff now. So first up, what we're going to do in this video, or this episode, we're going to talk about the branch and link trick, the BL trick. Really difficult to learn in my opinion, but once you understand it, this can be really useful for cutting down codes, making very complex codes and whatnot. Very handy. So what is the purpose of the BL trick? Why would we use something like this? So let's say, for example, you need to write large amounts of custom data, whether, for example, like a me name or something, a code regarding modifying a me name. So you have to write it from scratch, and you have to take it and put it in dynamic memory before the game reads it from dynamic memory. So this would be something like if you had a read breakpoint, and it was like a load word 0 instruction. So you would put that instruction at the bottom of your source. You would write custom data, in your assembly code, and then you need to put it in dynamic memory before you finish off the code. Now there are a few different ways to do it. I'll show you a method a intermediate type level coder might try to write it as, which would work in a lot of cases, but when you start to get a lot of word values like 8 words, 9 words of data, or 10 words of data, the method I'll show first starts becoming redundant and inefficient, so you'll start to use the BL trick, which is what we're going to learn today. So we're basically going to remake this code I made a long time ago called the friend roster plus your me, name changer, and extender. It puts a code that allows you to put a modified me name for you and your entire friend roster, and the ability to extend past the 10 character limit. So we're going to go ahead, let me copy paste this. Now one thing to note, that in this video this code is very unoptimized. So not only are we going to remake the code, we're going to remake it better, because I already know a few mistakes, well not really mistakes, just optimization issues. I could definitely be able to cut down this compiled code by at least one line length of code for sure. So first, I'm going to tell you, I already know when this code breakpoints. This code will obviously breakpoint when you view your name, or if you're already viewing your name, then you set the breakpoint when you go to view your friend roster. Whoever's in the first slot, doesn't really matter. So we're going to set a instruction breakpoint because we're working on a code that already exists. We don't need to go through dynamic memory searches to find it or anything like that. So there's the default me name I'm using right now. So let's just back away. We'll set our instruction breakpoint. Just like that. It will break the moment I press the A button, or right when it goes to the transition. Okay, so let's check out the code view. Here's our default instruction. So we'll go over what a intermediate level coder might do. I have my hotkey shortcut for stepping as the keyboard M, so if it accidentally steps when I'm typing this, I apologize, but first, a coder might do something like this. They might understand that there's an instruction called store multiple words, which they can use, but this would require pushing the stack, essentially. So let's just say the coder knows that in this case it's usually better when you have a read breakpoint to put the default instruction at the bottom. So a coder might write something like this. They're going to make a stack frame. This one we learned a long time ago. We get registers 14 through 31 to use them freely. That's incorrect. So store the word update, store multiple words, put R15 through R31. Okay, and then we'll just do the load multiple words like that, and then update the stack frame. So there's the push and pop the stack really quick with the default instruction at the bottom. So a coder might do this. Let's say they want to write, I don't know, Let's see. Let's just put some. They might write something like this. We're not going to worry about extending the me name for now. Let's just say now a me name is 10 characters in length in the game. Now to understand even further how long it is, let's go ahead and hook our dolphin. Now what the default instruction is doing, if we look over it, let's just go ahead and take this value. If you take this value right here, which you're already at in our memory viewer, actually slightly off, let's update it. Okay, so this is being part of the effective address used in the default instruction. The offset is 68, so we just start here. We don't need a hex calculator. This is easy to do. You just go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Now give you a moment to look at that while I get a sip of water. Okay, so what we got here? If you look to the right on Dolphin Memory Engine, you see we got a text ASCII conversion that we can always look at live on screen. Normally, hex ASCII conversion deals with bytes, but because Mario Kart Wii uses a complex system where they have to incorporate Korean letters, Japanese characters, special symbols, and whatnot, they use a half-word system so they can use a lot more combinations. And as you can see, this is the first half word of the me name, capital S. Here's the second. And then you have the third, the fourth, the fifth, the sixth, the seventh. This one only uses 8 or whatnot. 1, 2, 3, 4, 5, 6, 7, 8. Yes, so 8 half words. Even though, so a me name at the limit, the standard game limit without any modifications, is 10 half words or 5 words. So a coder might use a method where they're going to use R27 through 31 and use the store multiple word method. So they might write something like this. And they're essentially going to, this is like ASCII for 0, ASCII for 1, and they're going to do this for like 28, 29, 30, 31, for whatever me character values they're using, alright? So they'll fill up R27 through R31. This is assuming they're not going to extend the me name. And then they're going to do something like this. Okay, and then, now keep in mind, the store multiple word instruction has a caveat to it. There's a special rule to where this instruction is only valid, will only work if the effective address is divisible by 4 in hex. If it's not, this will cause exception and Broadway and crash the game. But let's assume this plus that is divisible by 4. I'm not going to double check if it is. Most likely it is. So they would do something like this. Now this might be actually pretty good code, but it'd be a little lengthy for one. We got to push and pop the stack, and we have these instructions. Why it might seem kind of clever that the intermediate level coder is doing the store multiple word instruction, it's not really all that clever because they have to do this repeating process, LIS or immediate, LIS or immediate, LIS or immediate. And this will especially be redundant if they wanted to extend the me name, where they start using registers like 25, 26, to make the me character 4 more half words in length. So thus they gotta do something like this, and then it just gets the code really redundant in length. So what would an advanced or a pro level type coder would do? Well, they'd use the BL trick. So first off, with the BL trick in this case, we won't need push and stack frames or anything because we're not going to be using the global variable registers. What the BL trick does is that it allows you to write data into an assembly source that doesn't use any registers, and they're not instructions, but yet they can still be used. And you're probably thinking this is some weird magical wizard shit, but I'll show you how we can do it. So understand that first, what is branch and link? Branch and link is it's an unconditional jump to an address. Make sure you have a valid address in memory, obviously. And then it links, it puts the return address into the link register. So let's say we have BL, I don't know, the 1, okay? But way down here, let's just say we have a bunch of ASM here, okay? Alright, and then we have your label name, the ASM contents for the one here, for the one is here, and then it's going to end off with a branch and link register. Now what happens here? Let's say we have an instruction that's directly under this, okay? Then we have our bunch of other ASM instructions, and you have your subroutine. So branch and link. Branch and link is an unconditional jump. It's going to jump here and execute the ASM contents that are right here. When it gets done, keep in mind at this moment, unless somehow the link register gets modified during this subroutine, the link register contains the return address. So once this instruction, branch and link register, gets executed, we go back to where we left off, right here. Does that make sense? So by understanding this, we can use this to precisely know, to tell the code where exactly in the static memory are we at. Because remember when I told you the code handler will take your ASM compiled code and dump the instructions to a spot in early and static memory? That place can vary depending on what code you have in your cheat manager, how the codes are listed, what version of the code handler you're using, whether or not using the Wii console, whether or not using Revo, Dolphin. It can vary. So we use this branch and link stuff to calculate it, so it doesn't matter where it's at in memory. If that makes any sense. So let's go ahead and do the branch link trick. Now, let me get another sip of water. The branch link trick obviously uses the link register. So when you're making a code with the branch link trick, you might have to back up the link register. So we're going to use the old classic method of looking ahead. So we're just scrolling down. We don't see any branches or loops, so we know the game's executing from top to bottom. We go ahead and look to the left of our code view. We keep going, we keep going, we keep going. And we see it loads a value in the R0 from the stack frame. Obviously you can tell we're at the end of a function call. Thus, it moves this value from R0 to the link register. So we can know right off the bat, because of this, and because we're at the end of a function call, the link register is safe to use. We don't need to back it up. So that's one thing I wanted to mention. In my old version of this code, I backed up the link register, which we don't need to do, which caused me to use R10, which caused me to restore R10's value at the end. So we have 1, 2, 3 non-necessary instructions on my current code in the forum, which I'll update after this video. So by the time you go and see it, it'll be updated. Okay, so that's how we're actually going to remake my code and make it better than before. Okay, so how do we start the branch link trick? With a branch link and a label name. Let's do the label. Now obviously you need your label name. And remember I told you the return address, the next step below the branch link, gets put in the link register. So we want that value to put it on the general purpose register, because we're going to make a loop after this, and you guys should know everything about loops, because you should be at the point where you watched all the previous episodes, so you should already know about loops, accounting for offsets, updating, loading, and storing instructions and whatnot. So I should not have to recover that in this video. So we want to put it in a general purpose register. You guys know about register safety protocol. We'll use R12 for that. So with branch and link trick, we have these things called pseudo ops. The ability to write data and ASM sources without using instructions and without using registers. Sounds like wizardry, but it's not. So essentially, we have these various titles we can use. Okay, so let's go with this first one. This equals a word value. So if we wanted to write just all zeros, compile zeros a word, or excuse me, double word. This is a double word. 2 words. So 1, 2, 3, 4, 5, 6, 7, 8. So if you wanted to write like a double word value here in the code, pre-compiled per se, this is how you do it. This is a word. Obviously you guys know what a word is. We don't need to explain that. Half word, byte, duh. Now we'll cover string in a second, but this one space, like if we had space 1, equals 1 null byte, or a byte of zeros. So space 2 would be 2 bytes of null, and 3. And 4, you wouldn't need to use 4 because you can just do dot long with all zeros. And what is dot 0? Same as space. 0.01 would be a byte of null, 2 bytes of null, 3 bytes of null, 4 bytes of null, 5 bytes of null, etc., etc. Okay, now string is something like, maybe you're making a complex code where you're messing with NAND files. You could just put text.txt. Now keep in mind there's alignment issues when you're working with this. Everything has to be word aligned. So you got to take how many bytes you got and be able to transform that to amount of words. It has to be an even whole number amount. So if you have alignment problems, you can use like the dot space dot zero. So if you just have something that's just like a string of text, and let's pretend this isn't aligned, you can use like dot space, dot 2, dot 3. It's either going to be 1, 2, or 3, because it'll never be 4, because if it's 4, it's already word aligned. Because when you write a string, when it gets converted into like X ASCII byte, the string pseudo-op automatically appends a byte of null afterwards, just as FYI. So if you're getting an alignment issue, like it's saying address is not divisible by 4 in your compiler, you might have to do dot space 1, dot space 2, dot space 3. One of those 3 options, and they will work and compile the code and fix the alignment issue. Now that we've gone over various pseudo-op titles and alignment issues and briefly covered the string pseudo-op, now of course you could write your customized me name in a dot string thing, but we're going to use hex just to not worry about strings and appending null bytes and alignment issues and shit. So first thing first is the whole purpose of the branch and link is to establish data in your ASM code and put it in dynamic memory before the game or the default instruction starts messing with that particular area in dynamic memory. Now in our looping episode about loops, we used loading and storing words while using the update feature. We're going to be using half words since we're dealing with half words in me names, and I'll explain more why later. So since we're using half words and we're going to use the updating loop, we need to offset a 2, a gap of 2 before the first half word value, the me name character, the first me name character beforehand. So our loop, when it stores data after it loads it, we need the first loop address to point exactly here. Now obviously we need this gap of 2, this gap of half word, to compensate for our loading in the loop before we store it to dynamic memory. So with all this being said, I know this is a lot to take in, we need to write a half word of zeros. Dot short 0x0000. Okay, now let's go ahead and write our me name. We'll do one word at a time to keep it simple. We'll make the me name, and we'll go ahead and extend it too. So we'll put in 11 characters on the me name instead of 10. Obviously, if you guys know about ASCII and conversion, this is plain 0, this is plain 1. Remember what I talked about? Each me character is a half word. Okay, so that's why it's 2 half words right there, 2 me characters. Oh, don't want to mess that up. I already messed up enough sources already before. Now, I'm going to do something a little out of the ordinary, not explain, but I'll explain afterwards. We'll just append a 1 at the end. Actually, we'll make this 12 characters in length, just for the hell of it. Because I'm going to show you alignment, if you need to do alignment, and something else. Now, so for starters, we got all our pseudo-op titles filled in. Everything is word aligned because a half word plus a half word is a word and everything else is a word. So this will compile. It won't put any alignment issues. Now the game, I know this from working with the game a lot. Now when you're doing branch link stuff and it doesn't deal with something like the me name like this, you don't have to worry about this right here. I put this here, and I'll explain why also again here in a second, that when the game loads the me name, it basically stops loading the me name when it reads a null byte or a half word, actually probably a half word of null. So when the game reads a half word of null after reading the me name, it knows to stop reading the me name. That's a game specific, me name specific thing. So this is why I have this here. And also we need to add this here for alignment purposes. Okay, so now, let's see. We got that there. So when we make this loop, we actually are not going to use a countdown register, and you're probably telling me, well, Vega, how are we going to be able to tell the loop when to stop if it doesn't have some sort of countdown register? Well, remember I told you the game, if it reads a null half word of hex for the me name, it stops. So we can do the same concept. We can just do a little check when we load these half word values, and the moment it loads a half word of null, it'll stop the loop, or stop right afterwards. So one thing we have to account for though is we have our beginning address of our loop with the offset of 2 gapped for the half word, obviously. Now we got to account for where we're storing all this data, which is here. So we got to make the first loop storing address, because we're using half word updates, point right here, just a half word before the first me name half word. So notice if we scroll up to the default instruction, R4 plus 68 in hex points to right here. So we just need to do R4 plus 66. So we'll go ahead and do that. And we can use R5 100% safely because obviously the default instruction. So this will set up the first looping storing address. And now let's just make the loop. Load half word 0 update. We'll use R11. Obviously offset a 2 for the half word. Load it from R12. Store the half word. Load a half word. Store the half word. Don't forget half words for half words or words for words, bytes for bytes. Okay, and check this out. Compare to 0. If you want it, it's just for better visual representation. We'll just put a half word to 0. Then branch is not equal the loop. And there, this is actually the code's completed. But let's go over it. Branch and link jumps right here, and the link register at this moment in time, right here, will point at this byte. Okay. So then we take the link register, it's pointing right here, we put that value in R12. Alright, so that's going to set up our first loop loading address. We then set up our first loop storing address, which points to dynamic memory. And look what happens. When we load the first half word value into R11, look, R12 plus 2, okay, this plus 2 points to this half word. We load this half word, it increments R12 plus 2, so we load this afterwards, and so on and so on. The loop loads, stores accordingly, repeat, repeat, repeat. The moment it loads this first half word of null, loads it, stores it, it's going to stop because it's going to do the comparison and see it's null, it's equal. Since it's equal, it goes down to the default instruction. So we also went ahead and made the accomplishment of storing that necessary half word of null to dynamic memory that the game needs when it's reading me names. So with all of this being said, let's go ahead and copy it. I'm going to double check one more time, make sure we got everything. Branch length, the label, alignment, me name contents, null, put in R12, add 66 to R4, R5, load R12, store R5, R11, 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 default instruction, make sure that's correct. We are good to go. This is something I compiled earlier when I did my first take on this video and I messed up. Alright, we got our source. If everything's right, it will compile. We got our address from the code view right here. Compile. We got our code. Alright, so now we got that done. Let's go ahead and stop this emulation. Okay, so now let's go ahead and apply the code. Just call a bunch of random shit, don't matter. Control A, Control C, Control V, and if everything goes correctly, so obviously you can tell by the compiled code and the compiler, we really made this code really short. If you were doing like the conventional intermediate level method, pushing, popping the stack, doing all that garbage, the code would be really lengthy. Okay, so now connect online, sip of water like usual. Yeah, I would say the branch link trick is probably the toughest thing to learn in ASM. Can be confusing, and as you can see, it works. 0, 1, 2, 3, 4, 5, 6. I had 2 things of 7 in there. Oh, I had 2 things of 7 in there. Oh, whoops. Doesn't matter, but the point is, we got the code working. We also extended past 10 characters the limit. We put the appropriate null byte or null half word that needs to be stored to dynamic memory, so the code will function correctly for how the game reads the me names. And that's really about it. So if you want to go ahead and step through this code, we can go ahead and do that. Why not? We can go ahead and step through it. Let's go set a breakpoint on this. And after stepping through, I'll end this video. But if you already understood it, you don't need to step by it. You can go ahead and end the video right now. Okay, as you guys should know, ASM codes are actually subroutines created by the code handler. Let's go here. Let's hook Dolphin Memory Engine up. There we go. We need the link register shown, so you guys know about the link register. Okay, so let's start off. Okay, branch and link. Obviously, it's going to jump to here. It's going to put this address of 8024 EC into the link register. Watch the link register once I do this execution of this instruction. As you can see, link register changes to 8024 EC. We put that in R12. We set up the storage of dynamic memory, the point right here for now. So when it stores the first half word, it stores there. Okay, go right here, store there. I'm going to fill this with F bytes. Just so you guys know, you can see it happen live in action. And store the last half word. Okay, so now as you can see, if we scroll up, see there's our branch link table type of deal. Alright, pretty simple. And this is from a word value of 0 because the two half words in null created that little dash 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 right there. So we load the first half word in the R11, store it, look to the right, look what happens. Compare to the current me name value that's being loaded. It's not 0, continue. Alright, boom. Watch to the right. We're doing our loop. Hopefully I don't jack this up or something crazy will happen. Okay, load, store. Alright, now watch what happens. Notice how it loads the half word of null, stores the null, which the game needs right here. Okay, compares it. Oh, we have a null, R11 is 0. Stop doing the loop, execute the default instruction, and then continue back where we're left off. And as you can see, the rest of the code, or the rest of these instructions in the game, will start loading from this spot in dynamic memory, which we modified, which is what the whole purpose of this code was. Go ahead, bomb the breakpoint, completely wipe it. I don't know why this is there. Okay, bomb it. Continue emulation. And we're there. Okay guys, that is a very lengthy, complex tutorial on the branch and link trick. Probably the toughest thing to learn when you get to this higher level of assembly and whatnot. So alright guys, that's it. Thanks for watching.